Now we're taking a look at electric forces. Let's go ahead and transition into what happens if you have charged particles and they're near each other. We've already discussed that electric forces can get bigger or smaller if you're closer or further away from an object, or if the amount of electric charge, the Q value, goes up or down. But likening this to gravitation, we're going to bypass this big ugly equation. Let's go back to that idea that if a particle with mass is near another particle with mass, or say something small like a tennis ball is near something big like the Earth, you're going to see one object seems to accelerate towards the other. In reality, they're both experiencing the same force towards each other, but there's what we call potential energy between them. They have the potential to go into motion if they're free to move. Same thing will happen with electric forces. If you have a charged particle, let's say a positive charge near a negative charge, if the positive charge is free to move, it will be attracted to and move towards that negative charge. So it will have a potential energy based upon where it is relative to where it wants to be. The problem is that charged particles are really, really small, and they carry a very small amount of electric charge. I mentioned before that 1 coulomb of charge was defined as an idea before we knew what the heck an electron or a proton was. So they just said, like, whatever happened in this second here, let's call that a coulomb. Whatever. However many charges moved through the wire, the light bulb, it's called a coulomb. So we came up with that idea, and then, long time later, we figured out that 1 coulomb of charge was really made up of a whole lot of charged particles. In fact, it's 6.25 times 10 to the 18th particles, which, if you write it out as a decimal, is this monstrosity of a number. All right, more money. If those are dollars, you'll never see that much money. That doesn't exist. So that's how many electrons or protons make up 1 coulomb of charge. It's ludicrous. It's billions of billions. And that means if you were to take 1 coulomb of charge and divide it by that many particles, you get the charge per electron, or charge per proton, which is 1.6 times 10 to the negative 19th coulombs. Now, I say here in the notes here, copy the numbers, because we'll take a look at them, we'll use some of them, but it's a pain in the butt to use this number. We'll use it, we'll record it, it is important, but it's not the most important thing in the world. What is important is this idea of what we've been calling voltage, is really this idea of electric potential. So it's not just potential energy, it's potential energy per unit charge. So we're going to take that classic concept of potential energy, the joules that something has by virtue of its location, and divide it by how many charges there are that have that potential energy. So it's really a rate. We've talked in the past about voltage, or volts being energy. Well, they are in a way, but they're not just energy. They're energy per unit charge. So it's a rate of energy that's going to be delivered to something. So when we talk about the volts going into a light bulb or coming out of a battery, it's the energy per charged particle. So it's pretty much energy with a caveat. So that idea of 1 volt being some sort of measurable quantity, let's go ahead and write out what the units are here. If it's potential energy is measured in joules. Oops, I spelled joules wrong. It's been a while since I've written that. And divided by the quantity of charge unit, which is the coulomb. So joules per coulomb is what we define as a volt. Not exactly something that like rolls off the tongue there. I apologize. Looks like I got a little bit of that delay in my writing. So 1 volt is 1 joule per 1 coulomb. We never refer to it as that. I often just call it a type of energy because it's convenient. But if something has more energy per unit charge, like a charged up battery, each charged particle at least has more energy that it can use to get around the circuit and make things light up, we'd say it has more voltage. It's got more desire to move. The charges want to get away from where they are. They have more potential energy per unit charge. So let's go ahead and do a couple of example problems using this new idea, this new equation. Example 2 here says a battery has a voltage of 4.5 volts. The charges in the battery have 10 joules of energy. What quantity charge is available? So essentially we're saying that we've got some sort of something like a battery, and there's a bunch of positive charges on one side, negative charges on the other, and we want to figure out just how much charge there is available to go into motion in this circuit. As I'm saying that, there we go, there's the little battery popped up. So we're going to identify things kind of how we did before. Volts is going to be the measure of voltage, so that's going to put V is equal to 4.5 volts. And then we'll go ahead and put in the energy as well. And the charges have 10 joules of energy, so go ahead and write in 10 joules, and we want to know what quantity of charge it is. So Q is going to be our question mark there. How many coulombs of charge is it? Again, it's not electrons, it's not protons, it's how many coulombs of charge. So in this case, we can go and write out the equation. We've got voltage equals, or electric potential, excuse me, equals potential energy per unit charge. We want to know what Q is, so we can go ahead and multiply the Q up and divide by the V and get the equation PE over V. So we can take that potential energy of 10 joules and we can divide it by the 4.5 volts and we get a number. I'll go and bust out my calculator right here. So 10 divided by 4.5, I get 2.22222. So 2.22 coulombs as we wait for the system to catch up there. There we go. Now, that's pretty straightforward, not using any of the funky mathematics. What if we were to switch it up though and bring up that whole electron thing? So how much potential energy would a single electron have if its voltage was 1.5 volts? So granted, this problem, we got 2.22 coulombs of charge. That's billions of electrons. So if one single electron were in a battery and it had 4.5 volts of energy per unit charge, how many joules of potential energy would it have? That's what we want to figure out. What's the PE? So let's go ahead and set that up. Go ahead and put in some numbers here. The voltage would be 1.5 volts. The potential energy is what we're looking for. And let's go ahead and see what the charge was, because we need the Q. We can't have two unknowns. So if I scroll back up, I got this ugly thing, 1.6 times 10 to the negative 19th coulombs. All right, so let's go ahead and write that down here. Q is equal to 1.6 times 10 to the negative 19th coulombs. And if I want to try to solve for the potential energy, let's write out the equation. Voltage, or electric potential, is equal to the potential energy divided by charge. And if I wanted to get to the potential energy, I can just multiply both sides by Q. So potential energy will be V times Q. And in order to do that, I'm going to have to type that stuff into a calculator. 1.5 times the 1.6 times 10 to the negative 19th coulombs. So I'm going to get my calculator app going here. Let's see, swoop it on over there. And let's go and do a little refresher on how to type this stuff in. 1.5, that's easy. 1.6, that's easy. But the times 10 to the negative 19th. So on one of these here calculators, I can do, let's see, parentheses. I'm going to put parentheses around my numbers here too, just to be safe. Parentheses 1.5 multiplied by parentheses 1.6. And then to do this, remember we had a couple ways of doing it. There was the times 10 to the X button, there was actually typing out times 10 to the whatever, or there's the EE feature. I'll go ahead and use the times 10 to the Xing, so I'll put times, then the 10X, and then I'll put negative 19. The negative is really important there. I gotta do a bunch of empty end parentheses. And I get 2.4 times 10 to the negative 19th. So that's what my potential energy is. That's like nothing. That's how many joules of potential energy I got. And I got to go ahead and write this down. Oh, this screen keeps screwing up. There we go. Caught up to me. So that's like nothing. If you were to put this in and type it in as a decimal, let's see what it would be. That would be 18 zeros. So you go point 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 2, 4. That's how much. I mean, that's a rounding error, right? So one single electron does not carry very much energy. But billions and billions of them together do carry a lot of energy. So that's why when we have 1.5 volts, it doesn't sound like much, but that's a whole lot of charges that have that energy, and they can do a lot of work. They can make things light up, they can make objects move, motors, all that kind of stuff. Okay, let's take a look at electric current. A little break point there between voltage and current. We want to define what electric current is. We talked about it just as the rate that charge flows in some sort of a conductor when it's hooked up to batteries or some sort of voltage source. But let's go ahead and take a look at it from that idea of what an ampere is. An ampere is the amount of charge per unit time flowing through a circuit. It's the rate that charge flows. It's not the speed. It's the rate that charges actually flow. So that's going to be the units for charge quantity, coulombs, divided by the unit for time, which is seconds. And so we'll say that a coulomb per second is equal to the ampere. I think it takes a while to catch up. So 1 ampere is 1 coulomb per second. Now we don't need to go too crazy with all this, but just for a little bit of practice, let's say that we had that 2.2 coulombs of charge from example 2. If I go back up, that's what we calculate right here. We had 10 joules of energy when the electric potential for the battery pack was 4.5. We said that must have been 2.22 coulombs of charge. So if the 2.22 coulombs of charge in the circuit flows through every 2 seconds, what is the current? Well, current is going to be charge divided by time, so currents are question mark. The amount of charge is 2.22 coulombs, and the time is 2 seconds. So we can go ahead and calculate I equals Q over T. It's catching up to me. There we go. And we'll take 2.22 coulombs over 2 seconds, and I can do this one without the calculator. I don't even need to back it up. I'd have 1.11 amps. Or is it catching up? There we go. So I can calculate the amps right there. Let's do a couple more practice problems here. I got the answers over onto the side. Some of these are review questions. So look at this one. 4 ohm resistor is connected to a 3 volt battery. How much current flows? Interesting. Should be 0.75 amps. I'm not going to do that one. You do that one. You should be able to do that. Number 2, a total charge of 340 coulombs move through a circuit every minute. What is the current? I don't know. I think that one's pretty easy too. I think you should be able to do that. Catch here though, is it says every minute. Got to remember that that is 60 seconds. So I've got the charge quantity, 340, and the time, 1 minute. And I need to figure out what the current is. So I'm looking for I. I've got the charge quantity and I've got the time. I think I can use that equation that we just had. Should be able to get 5.67. Go ahead and do that, see what you get. Number 3, if the total quantity of charge number 2 has 12 volts of voltage or electric potential, what is its total potential energy? So we've already got the total quantity of charge, that's the 340. We're just going to borrow that number down here. So we still got Q. And we've got the voltage or electric potential is 12 volts. And we're trying to find out what the potential energy PE is. I think that one's pretty straightforward. Hopefully you think it's pretty straightforward as well. Try to calculate it out, see if you get 4,080 for that. And this one, let's go ahead and do this one together though, because for number 4, it's got this scientific notation. It's the tricky stuff. We're coming up on 15 minutes for this video, so I'm kind of wrap it up with this problem. It says a single electron has a total energy of 4.8 times 10 to the negative 15 joules. What is its voltage? Single electron. The charge for an electron is the same as the charge for a proton. They both have the same amount of charge. It's this 1.6 times 10 to the negative 19th. Got it up here. Told you to write that down. That's super important. That number is really important. So the charge quantity we're dealing with for number 4 is just one single proton, or sorry, one single electron. So the charge quantity would be 1.6 times 10 to the negative 19th coulombs, that ridiculously small little bit of charge. The potential energy, they tell us, is 4.8 times 10 to the negative 15th joules. and we want to know what the voltage is. So to solve this, we're going to have to use the old calculator, but if we go and set up the equation, we have voltage is equal to potential energy divided by charge quantity, PE over Q. So we'll have the 4.8 times 10 to the negative 15th joules of energy divided by 1.6 times 10 to the negative 19th coulombs of charge. Whenever you're dividing by scientific notation, I always say it's a little weird. The numbers are a little awkward feeling. You got to give them a little reassurance, give them a little hug. So you want to put parentheses around that denominator. Just give it a little hug before you send it on its way, right? So let's go and get the calculator back over here and show how we're going to do that calculation. I'll do 4.8 times 10 to the 15th. I'm doing a little EE notation in this case. Divided by parentheses 1.6. I'll go and write out the longhand, times 10 to the power negative 19. So as long as you put parentheses around that denominator, you should be okay. And I get 30,000 volts. Now, what happens is sometimes people type it in incorrectly and they don't get 30,000. So if you're not getting 30,000, you're making a calculator mistake. Don't do that. Try to correct it. We'll have to work on that together in class at some point. But that's the setup for these problems and continuation of the notes. So hopefully this will allow you to work on some of those assignments. And if you got questions, make sure you send me messages.